Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Kent Berridge, who is a professor of psychology and neuroscience at the University of Michigan. His research aims for answers to questions such as what causes addiction, how are pleasure and desire generated in the brain, and how does fear relate to desire in the brain. Welcome, Kent.
Thank you, Gil. Pleasure to be here.
Yeah, thanks for doing this. So I want to start with one of your older papers entitled Liking, Wanting, and the Incentive-Sensitization Theory of Addiction, in which you say rewards are both liked and wanted, and those two words seem almost interchangeable. However, the brain circuitry that mediates the psychological process of wanting a particular reward is dissociable from circuitry that mediates the degree to which it is liked. That appears a bit counterintuitive. So what exactly do you mean?
Well, it was a surprise to us, and certainly nothing that we were ever expecting or looking for, that liking and wanting would be separated. I thought they were simply just two words for the same reward process in the brain, that what you like, you would want, and what you want, you would like. And we thought we knew the brain system. 30 years ago, we thought it was dopamine that did both liking. Well, it did liking, and so naturally you'd want anything that turned on the dopamine system because dopamine should be liking. There was great evidence for this. Roy Wise was the neuroscientist who really amassed the evidence for this in the 1980s, and I was utterly convinced by his evidence that dopamine was pleasure liking. In fact, Roy Wise and I collaborated at one time. He phoned me and said, well, you're looking at pleasure liking in a way that's different from other people. So why don't we do a collaboration and we'll try to suppress brain dopamine systems with a drug that blocks dopamine receptors, and we'll see if the pleasure liking goes down with your measure. Our measure was different from most in the field. Most measures of reward liking in the field are really measures of preference or effort to get the reward or consumption of the reward. In a sense, they're measures that are kind of based on wanting the reward. Our measure was more like the measure that human parents have used for thousands of years to ask their newborn infants, do you like the tastes of foods that we eat, by giving the infant just a tiny little bit of that taste in the mouth and see how they respond to that. So we did. Go ahead.
Go ahead. Go ahead.
So we did the experiment, and we blocked dopamine with a drug. We gave sugar tastes to. It turns out that rats who are omnivores like humans, they like sweet foods and they don't like bitter foods. They'll show positive lip licking and things to sweetness and gapes to bitterness. So we gave sweetness to the rats after giving them the dopamine blocking drug, and we thought their liking reactions, the facial liking, lip licking reactions, would go down, but it didn't. It just didn't go down at all. And I was slightly disappointed, but I didn't really believe the results. I thought we probably just did the experiment wrong. So we did it again, and we did it again, and we always got the same results. And I thought, well, maybe the drugs are just not strong enough. Maybe they block dopamine receptors, but maybe we need something stronger to reduce dopamine more than that drug would do. So my colleague Terry Robinson here at the University of Michigan was at that time doing dopamine brain lesions. There's a neurotoxin which, if you inject it into the brain, it will kill only neurons that express dopamine, that release dopamine as their neurotransmitter, and it won't hurt other neurons. It's called 6-hydroxydopamine, this neurotoxin. So we anesthetized the rats, and we eliminated basically almost all of their brain dopamine. We eliminated 98 to 99% of their dopamine, so they had only 1 or 2% left of normal dopamine levels. And these rats were utterly aphagic and adipsic. That means they wouldn't eat anything voluntarily, they wouldn't drink anything voluntarily, they wouldn't seek out any rewards or consume any rewards at all. There's like extreme Parkinsonism. So we really expected they wouldn't like the sugar anymore. We gave them sugar, and to our surprise, their liking reactions were absolutely normal. And they could learn new likes and new dislikes. We found that out too. So they seemed to have absolutely normal liking system in the brain, yet it wasn't being translated into wanting anything. And as a sort of a post hoc explanation, we said, well, maybe the dopamine is mediating the wanting for these rewards, but not the liking. But I didn't really believe that at that time. That was just a sort of post hoc hypothesis. And we went on with further experiments in the next few years to stimulate the brain dopamine system, which for me is much more convincing than taking away the brain dopamine system. If you stimulate a system, you can increase its function and you can see its function more clearly. It becomes stronger. So we would stimulate the dopamine system, and we found we could always enhance wanting for rewards. We could turn on and increase, but rats would consume more food, they would work more for rewards, but their liking reactions never went up with dopamine. So that put us there.
Yeah, so to get a better definition, so the established thought was dopamine was needed for liking response, and your experiments demonstrated that dopamine is not a necessary requirement for liking response, right?
That's right. That's what we thought.
Yeah.
Although it's probably fair to say that most of the world didn't believe us in the 1990s.
And so you wanted to test. So how do you differentiate between liking and wanting from a response perspective? Let's say the rat model.
Well, one way is by using these facial reactions to look at the liking for the sweetness. I mean, that's actually very useful because it's sensitive to not just sweetness and bitterness, this liking facial reaction of rats and apes and people. It's also sensitive to hunger and satiety, that changes liking for sweetness. When you're hungry, you like it more, and the facial reactions of the rats go up. When you're full, you'd like it a little less, and their reactions go down. They learn a taste aversion for a sweet flavor, a new sweet flavor, by having it paired with nausea a couple times. This happens sometimes to people, and they develop a learned taste aversion for that food. Even if they loved it the first time, they find after it's been paired with nausea a couple times, if it's a new food, they find it disgusting later. And the rats would switch their reactions from these liking reactions to gapes as though it were bitter. And vice versa. We can take disgusting tastes and make them liked. Something like seawater or Dead Sea seawater from the Dead Sea, which is 3 times saltier than seawater. It's disgusting, and the rats will gape to it. But if the rats are put into a state of sodium appetite, salt hunger, by giving them hormones overnight, it fools the brain into thinking they're sodium depleted. They wake up and now they like this Dead Sea seawater. They respond to it as though it's sugar. So it's a sensitive way of measuring the pleasure liking, as long as we can use tastes to probe that system. Wanting is different. I mean, wanting is consumption. It's measured in consumption of the reward. It's measured in working and effort for the reward and preference for the reward. The dopamine kind of wanting, it turns out to be a very specific kind of wanting. It's a subtype of wanting. We use incentive salience as the technical term, but what it really means is it's sort of cue-triggered wanting for things like drugs and sex and foods and consumer items where where the smell of food, the sight of food can be attractive to you, can make you suddenly hungry if you were not quite hungry before. And the sight of consumer items sort of lights up the same brain system. Sensory rewards and concrete rewards that have cues trigger the dopamine system, and it's that kind of wanting that it mediates. It's something that you want with the dopamine system. It's hard to ignore. You would have even involuntary eye movements in a eye tracking situation, so that grabs attention. These wanted cues, and they're attractive, and they can spur wanting to consume the associated reward.
So the wanting response is sort of instinctual, that is sort of system driven, a requirement?
Yes, it is, although it's also very much learned. The cues that turn on the dopamine system are almost all learned. Advertisers use this all the time for when they show us cues of fast cars or clothes or jewelry that turns on the dopamine system. These are learned cues, but they're very effective in us.
Learned cues. So that is what you've shown in rat models. You can actually sort of train them to want something. And once they are in that state, they will continue to want that, even though they don't necessarily like it. Is that the way to understand it?
Yes, in a sense, that's right. Although, if we turn on the dopamine system, say with a stimulating electrode that activates neurons, or by giving a microinjection into the brain of amphetamine into the brain's nucleus accumbens, it causes dopamine neurons to release their dopamine. What happens is the wanting goes up, but it isn't necessarily constant. It comes and goes with cues for reward. So if you have a dopamine elevated state and there's no reward cues, a rat doesn't show much wanting behavior. But if there's a cue comes, then it's massively enhanced surge of wanting that the dopamine stimulation creates. So it comes and goes. Now in people, imagery, vivid imagery, can substitute for physical real cues. So if we're thinking about the fast car that we want, that can interact with the dopamine stimulated brain and cause a trigger. But still, imagery and cues, they're the special keys that unlock this brain system.
Okay. So is there any sort of evolutionary basis for this? I'm talking about wanting specifically. Would they have had any sort of selection advantages if wanting is driven by cues? Would that have given early Homo sapiens some advantages from a selection perspective?
Well, it's speculative to think about the evolutionary explanation because, of course, we weren't there at the time, but we can think about it. I think it could give an advantage, but far, far earlier than Homo sapiens. This system is shared by all mammals. It goes back at least 60 million years. And there's actually evidence to think it's more widely shared and may go back a couple of 100 million years. The basic circuitry of the dopamine system. If a system can respond to food cues, to cues for a mate, that an early creature would be able to react, pursue, and propagate its genes. It would survive and propagate its genes. It could thrive with only a wanting system. If you had to have only one system, wanting or liking, wanting would allow you to survive. But a liking system, pleasant as it might be, isn't necessarily going to achieve any goals all by itself. It needs to be hooked up to wanting. So it makes sense if wanting were the original system, and it's more robust, the wanting system in the brain. It revolves around dopamine, but there's many more components, and it's large and it's robust in the brain, the wanting system. The liking system, we can find it, and we can stimulate it and see it. It's a more fragile system, and possibly the liking system evolved a little bit later as an adjunct. If you have liking, you can acquire new wants by experiencing a new event and having it liked and then having that assigned wanting to that. It may be that that's how it came up to be the two systems combined together.
So the wanting system is sort of foundational. It's almost like part of the operating system, and the liking system is more recent, works a bit like an application on the operating system. But you say that liking may have effects on the wanting system over time.
Yes, they're like hand in glove. The liking system is nestled within the wanting system. The liking system, it seems, is composed of little hedonic hotspots, tiny subregions within the nucleus accumbens, within the orbital frontal cortex, within the insular cortex, and a couple of other brain structures. And they're all connected together functionally. So if we turn one on, it turns the others on, sort of as a unanimous network. They come on together as these liking hedonic hotspots. Now, dopamine can never turn them on, but opioids in the brain, sort of natural heroin, opioid chemicals, and endocannabinoids, natural marijuana-like neurotransmitters, can turn on these hedonic hotspots, and the whole system comes on. It's nestled within the wanting system, these hotspots. So it can trigger itself. The liking can trigger wanting. That's something that often happens. Turning on liking often turns on wanting. But if we turn on wanting selectively, say with a dopamine manipulation or some other manipulations, it does not turn on liking. So usually liking will bring wanting, but wanting can happen alone.
Yeah, so the sub likings, so to speak, you say they all turn on simultaneously. So if I like cars and if I like the color red, then I would like a red car. So all those things are all those things are active when somebody likes something.
Yes, that would be our expectation. The actual data is from liking foods and sweet rewards and such, because we can still measure the liking reactions in the rats with those kinds of rewards. But the hypothesis, it seems from human neuroimaging studies that the same circuitry gets activated by foods, by drugs, by red cars, if you like red cars. So it's a plausible hypothesis that, yes, that's what's happening.
And so the biggest finding is that dopamine does not have the power to turn on the liking system, but it does have the power to sort of train the wanting system to behave in certain way.
Yes, that was the original fact that led to the incentive sensitization theory of addiction and things like that.
So what are the implications for addiction then? So the way that we treat addiction, there are so obviously, chemical agents that are used for this. What are the implications for the contemporary treatment of addiction?
Well, for a long time, it was thought that the essence of addiction was really dependence and withdrawal, and the nastiness of withdrawal states for people when they stopped taking the drugs, that would trap them into the addiction. And that was a dominant thought throughout the 80s and the 90s as well. But it was clear even then, that people could go into rehab situations, go through withdrawal and come out of withdrawal and be free from withdrawal, and then go back into the world and relapse again. They were not in any way protected from their addiction by coming out of withdrawal. What happens in the brain, and this was beginning to be realized in the 1990s, is that for some people who are taking addictive drugs, they don't just develop tolerance and withdrawal to those drugs. They also change the dopamine system in a different way, an almost opposite way. It's called sensitization of the dopamine system. One way to see sensitization is just look at dopamine release triggered by the drug. If a person or a rat has been sensitized by repeated doses of the drug, then the 10th dose of drug will get a much more large, robust dopamine release than the first dose did, even if the doses are identical, even if the drugs are identical. The brain is reacting more strongly to it. Not everybody will sensitize. Not every rat will sensitize. There's enormous individual differences. Some individuals are easily sensitized. Other individuals can take the drug again and again and again and never sensitize at the regular street doses that they're typically taken. So it's just the ones who will sensitize that this is going to apply to. But once sensitization happens in the brain, it doesn't go away. If you stop taking the drug, sensitization stays. And if anything, it strengthens in the month or so after a person stops taking these drugs. And it's still there. It's still there a year later. In a rat, it lasts half the rat's lifetime. And it's quite possible that in humans, it might last half a lifetime too. Once sensitized, you're more responsive to the drug. and also to cues for the drug. The sight and smell of the someone lighting up a cigarette, or the sight and smell clinks in the glass of alcohol, drug paraphernalia for other drugs, will trigger the system, and it's a dopamine kind of response. So it's a wanting urge response. So the general notion is that a sensitized individual is going to have stronger urges, stronger wants for drugs than other individuals who take the same drugs but aren't sensitized, and stronger than the rest of us have for virtually all rewards, because the sensitization is so intense.
And so it's not that the body's getting tolerance to dopamine. So if I understand this correctly, Ken, so as you go through the sensitization process, you have a higher and higher amount of release of the dopamine. And we actually see the effects of that on the model, right? Whether it's a rat model or human model. And so the body's releasing more dopamine. It's not that it's getting tolerance to it. It is actually getting higher and higher effect as it goes forward.
The complexity of the situation is that actually both things can happen simultaneously as long as the person is taking the drug. There can be tolerance and there can be receptor downregulation, which means that some of the dopamine receptors go away while you're taking the drug. That produces tolerance and contributes to withdrawal. But if you stop taking the drug, those changes mostly come back, so that the downregulation of dopamine receptors mostly comes back, and there's the withdrawal and tolerance goes away. But the sensitization changes are mediated by other molecular changes in the neurons, and they don't go away. They stay.
Yeah, so two effects. One is the downregulation comes back, but the body is still releasing the same amount of dopamine, and so you have a much more enhanced effect once you come back.
Yes, that's right. Now, I said that probably most of the world didn't believe us throughout the 1990s, and it's really only been in the last 10 or 15 years that there's been much more citations of the theory and belief in the theory. And one of the things that happened was a sort of diabolical but inadvertent medical experiment that hinged on the development of new medications for Parkinson's disease about 15 years ago.
Yeah.
And it essentially can create addicts out of people who were never addicts before. The old classic medication for Parkinson's disease is L-DOPA. L-DOPA helps neurons make dopamine and release natural dopamine. But there are consequences to taking L-DOPA for years, and so drug companies searched for alternatives. The new medications are not L-DOPA. They're sort of like fake dopamine. They don't need real dopamine. They can plug right into dopamine receptors themselves and turn on dopamine. These are called direct agonist medications. They turn on dopamine D2, D3 receptors. So you don't actually need any dopamine. And they're marvelous drugs to help people with Parkinson's disease. But at least 15% of the people who are taking these direct agonist medications, especially if they're taking high doses, start to develop motivational compulsions to gamble, to shop, to pursue sex and pornography, to pursue hobbies compulsively, say at 3 a.m. in the morning, and sometimes even to take their medication in extreme doses, essentially become addicted to the direct agonists and the L-DOPA medications. And these aren't incredibly pleasant medications, but they become wanted, and all of these things become wanted. And these were people who were never sort of risk takers or certainly not addicts before, but it's creating this in them, these medications. And if you finally take two Parkinson's patients, one who has these motivational compulsions called dopamine dysregulation syndrome, and another who doesn't, and you put them both into a neuroimaging scanner and give them each of them a dose of L-DOPA to stimulate dopamine release, what you see is that the ones who have the compulsions release more dopamine to that drug than the Parkinson's patients who are also taking those medications but aren't showing the addictive-like compulsions. And what that means is that the ones who are developing the compulsive motivations have become sensitized. They're showing the higher dopamine release to the same drug stimulus. And that seems to be causing their addictions, this extra activity in the dopamine system.
So it sounds to me, Ken, that I can't find too many good things about dopamine. What exactly does it accomplish on the body?
Well, dopamine is a wonderful, wonderful thing. For one
Yeah.
thing, it gives zest to life. When you find life inviting and attractive and it spurs you on to do things, when you walk out of the door in the morning, it's dopamine that's helping to give you that. Dopamine also helps us survive just as it helps our ancestors survive. It is what makes us want food when we're hungry and makes us want other things. It's a useful, in moderate amounts and in the right times and at the right degree, it's a very useful function. But if it intensifies beyond that optimal range, it can be problematic.
Yeah, I wonder, Ken, whether it's a design gone not wrong necessarily, but less useful in the modern context. So I can understand early on you needed the wanting system to kick in for food and sex. But in the modern context, we always say only eat if you really, really like it. This idea that you have to have 3 meals, all of those preconceived notions are actually creating problems for the modern human. And so has the wanting system gone sort of haywire in the modern
Well,
context?
the modern context gives us many things to like and to like very much. Foods are delicious. There's sugars, there's fats, there's artistic cooking techniques, so food becomes delicious. And also the modern world is cue rich. It's loaded with cues for food, for other things that tempt us. And yes, in the modern world, we are continually tempted, and it's our dopamine system that allows this to happen. And for some of us, that has problematic consequences. We become overly tempted.
I want to go into one of your recent papers. It's entitled a Liking versus Wanting Perspective on Emotion and the Brain. It's a book chapter, I believe, right? So you say reward, pleasure, threat, fear, and disgust are emotional labels that we often use with confidence as if we knew the identity of their corresponding psychological processes. So you're arguing that many of these things are related and often misused. I want to talk a bit about that.
Sure. Is there something particular that you have in mind?
Yeah, so you say that the psychological processes of emotion are quite real and deeply grounded in brain systems shared by humans with many animals, but the identity of fundamental psychological components within emotion are sometimes mistaken because only the final products are experienced, losing the identity of important psychological components that arise en route. And so what do you mean by we only observe the outcomes, but not the processes themselves?
Well, we find surprises, psychological surprises, as well as brain surprises from this research. One surprise was that liking and wanting really were so separate. We don't experience them as separate. We experience them together, so that we find it almost hard to imagine that they really are separate, and yet the data say they are. Likewise, there are surprises in the psychological components of fear and desire. Now, those two seem very, very separate and opposite. You'd never lump them together, fear and desire. Fear is negative and nasty, and desire is positive. But it turns out that some of the brain systems can overlap, and there are actually some shared psychological components to perceiving something that rivets your attention and you want it intensely, it tempts you, versus perceiving something that rivets your attention, but it threatens you and it frightens you, but you can't not look away from it. It's that riveting. The nucleus accumbens and the dopamine system are participating in both of these. And there's even evidence to suggest that activating the same neural system can be flipped into either desire or fear, depending on psychologically what's going on around us at the moment. So it's saying that there's something shared between fear and desire shared in the brain and shared as a psychological component that we don't quite experience as shared, but because we finally experience the full final product of fear and desire, we don't notice the shared component within those two entities.
Yeah, I mean, people like horror movies, right? And it's sort of difficult to explain why. But there's set of emotions, a very complex set of emotions that are created, and so this could be again. They might have been some survival advantages early on, but in the modern context, it might be sending confusing signals. Is that?
Yes, I
Yeah.
mean the brain evolved to function and to use components in ways that would work, but not necessarily in optimal ways. So there is something efficient about evolution using the same brain system for a sub process of fear and a sub process of desire, because both of those things, they do capture the attention, they're motivationally very powerful. It makes sense that some of the same circuitry can be involved in a sense. But the valence is utterly opposite. And that's something we're trying to understand now, is really what's controlling the valence, the goodness or the badness that makes desire positive and fear so negative.
Mm. So does it have some implications again for treatment of mental diseases? I'm thinking schizophrenia or something like that. Is there any connection
Well,
there?
there seems that there is. This isn't a hypothesis that I posit or my colleagues here have posited, but other people who are studying schizophrenia have suggested this. And in essence, it turns out that some aspects of paranoia are using brain dopamine systems similar to the way we can create fear in rats by stimulating brain dopamine related systems. There's a suggestion that the paranoia is being driven through this sort of fearful salience. It's the cousin of incentive salience, the nasty cousin of incentive salience, where percepts and thoughts capture our attention, but they seem very threatening to us, and so they become incorporated into the narratives that people are building, often of persecution about them. And if you can suppress the dopamine system, the usual medications for schizophrenia are antipsychotic drugs, which classically are dopamine blockers. They're antagonists of the dopamine system. And even the new atypical antipsychotic that also block serotonin systems, they still block dopamine systems. And there is a thought, Satish Kapoor is a psychiatrist currently in Australia, I think, who's suggested that if you give the antipsychotic drug, what happens is that it reduces this fearful salience, it reduces the motivational compellingness of the contents of the paranoia. The delusions don't go away instantly. They don't go away with the suppression of the dopamine, but the motivational potency of those delusions might be weakened by the antipsychotic drugs. And the thought is this might provide a kind of space, a psychological space, for other means to help dissipate the delusions of schizophrenia.
Yeah, I mean, the downside, obviously, many of the CNS drugs have side effects that sometimes difficult to predict, and so that's the downside of these types of interventions. But I also wondered, is there any connection again, because dopamine is involved both here as well as in addiction. Do we see some correlation between people who are more prone to addiction to having these type of um, psychological diseases?
Well, there's definite individual differences in being prone to addiction, and also definite individual differences in in these various diseases. But and there may be some overlap, but they are distinct things, clearly distinct things. And the genetic inputs that say foster schizophrenia are not necessarily identical to those that foster addiction. So they are if they overlap, they are still distinct things.
Hmm. But if you treat schizophrenia, for example, with something that reduces dopamine in the system, presumably that will have an effect on the wanting system, right? Wouldn't it surface in some
Yes, I
other
think it
way?
does have an effect. I mean, one of the famous things about antipsychotic drugs is that people don't like to take them. They reduce the enjoyment of life. They reduce the zest of life. And that makes sense. If you are suppressing the wanting system, you're not just suppressing it, the motivational compellingness of paranoid delusions, but you're also suppressing the motivational compellingness of everything in life, or rewards, incentives, social, loved ones, aspirations, all of these things dimmed. And that's not something that anyone really wishes to have. So people are reluctant to take these drugs, and for legitimate reasons.
So dopamine is sort of a blunt instrument in the sense that it has so many different effects on the brain. Uh, we haven't really been able to get deeper into that. So it is just dopamine. It's not components of dopamine or the sites it's acting. We haven't been really sort of affected in a refined
Well,
fashion.
it's probably best to think that dopamine is like a domino in a chain of dominoes that all fall over. Dopamine is a really visible domino. It's a linchpin in this circuitry, in this chain, but there's many other components, neural components too, besides just the dopamine neurons. It's the circuit as a whole that's doing this. Now, dopamine has been handy. It's easy to manipulate in science experiments, and it's also the target of drugs that are given to people as medications and as addictive drugs. So it's so visible in its effects, but it's changing the whole circuit when we change dopamine. It's not just dopamine. Now, is it a subcomponent? It's true there's multiple subcomponents, there's multiple receptors for dopamine, and they are playing slightly different roles, absolutely. But I wouldn't want to just blame any one particular receptor. There's evidence that multiple ones are involved.
Yeah, I want to touch on another paper, Ken. So the central amygdala recruits what is called mesocorticolimbic circuitry for pursuit of reward or pain. You have a rat experiment here. How do brain mechanisms create maladaptive attractions? You want to describe the rat experiment? I
Sure.
found that very
The reason
interesting.
we're doing this experiment, which is using laser light, the new optogenetic techniques to activate neurons, to stimulate neurons. We're stimulating neurons in the amygdala, but they're recruiting stimulation of neurons in the whole dopamine circuit. The reason we're doing this is because in addiction neuroscience today, I think we have a fairly good understanding of what's controlling the intensity of desires, but we do not have a good understanding yet of what's controlling the direction and the focus, the narrowness, or the breadth of focus of a desire. So, normally in life, when you're hungry, you want food. When you're thirsty, you want something to drink. At other moments, you want something else. So the focus of your wants change. And in addiction, the focus of the want becomes sort of more intense and more narrowly focused on just that one thing. What's controlling that? That narrowness of focus. And the amygdala is a part of the brain that interacts with learning very, very much, and it interacts with perceptions very, very much. It's sort of involved in recognizing the motivational significance of percepts in the world that we encounter. So we're manipulating the amygdala to try to recruit the dopamine system. And what we're doing, we're finding if we pair this stimulation of the amygdala, we can create a sucrose addict out of a rat who wants sucrose only and will ignore intravenous cocaine. Nothing magic about intravenous cocaine when it's pitted against this laser stimulated sucrose. We can also create a different rat who's a cocaine addict who wants only the cocaine and ignores the sucrose. That's probably more intuitive, but the same amygdala manipulation will do it. And a little bit to our surprise, but it turns out to be very, very revealing. We can even create a maladaptive attraction to what hurts you, to what only hurts you and what has nothing good about it at all. So here's the experiment with the rat. In this case, the rat's put into a chamber. It can wander around, and sticking out of the wall of one end of the chamber is a rod a few inches long, which the rat can come and touch if it wants, but it certainly doesn't have to. It has plenty of room in the chamber to walk around. Now, a normal rat will come and touch the rod out of curiosity, and this is a shock rod. If you touch it, you get a mild electric shock, and it'll only last maybe half a second because the rat instantly jerks away. A normal rat will touch it once, maybe twice, and then it will stay as far away from that shock rod as possible, very reasonably, and it will even show anti-predator reactions to it. It starts to kick sand at the rod and it can bury the rod. It's an anti-predator reaction. But the rat who has the laser in the amygdala that stimulates the amygdala every time the rat comes to within, say, half an inch of this rod, this rat gets the shock and jumps back. But it comes right back and sniffs that rod very eagerly and gets another shock and jumps back. And it will come back and just hover over the rod and hover, get closer and closer, sniffing, touching with its paw, touching with its nose, and it will get shock after shock after shock, jerking away each time, but irresistibly attracted and fascinated by this rod. So fascinated and attracted that it just incurs more and more shocks. We take the rat out so that it doesn't get too many shocks, but it would keep on going and do this. This is a maladaptive want. It's a want for what's hurting the rat. And the hurt is actually a part of the want, because if we give the rat a dummy rod, an identical rod, but not hooked up to any electrified shock, the rat does not become attracted to that. It's something about the shock is similar in a way to the brains, to sucrose or to cocaine, to sugar or cocaine. All of these are emotionally powerful stimuli that can activate the mesolimbic system, and if they're paired simultaneous with this amygdala stimulation, they become irresistibly attractive and specifically attractive. We narrowly focused the wanting upon this one particular thing. It's also probably, go ahead, Gil, sorry.
So mechanistically, how is it done, Kent? How is the laser stimulation
The laser
done?
stimulation is done in a couple of steps. The first step is to make the neurons in the amygdala sprout photoreceptors. And the way that that's done, we have photoreceptors in our eyes that respond to light striking our eyes, the retina of our eyes. The molecular configuration of the photoreceptors changes when light hits those photoreceptors and they turn on neurons. What we can do with the amygdala using optogenetic techniques is to anesthetize rat, do a microinjection of a tiny droplet of a virus solution that contains the gene for a photoreceptor. And we put that tiny droplet into the amygdala. Now, this virus, it's not like the COVID virus. It can't spread throughout the body. It can only infect the neurons where the droplet is. It can't reproduce. But it will infect those neurons in the amygdala where the droplet is, and it will implant into the nucleus of the neurons the gene for the photoreceptor. The neurons in a few weeks will make the photoreceptor and will sprout the photoreceptor. And now, if we have a laser light in the same surgery, a tiny optic fiber was implanted in the amygdala. If we connect that to a laser and we shine a blue laser light into the amygdala neurons, now they will fire. They'll be stimulated just as our eyes are activated by light striking the retina. So this is what's making them fire. Every time the laser comes on, the neurons fire. If the laser goes off, they stop. It's firing the amygdala.
Yeah.
But it's really also, it's recruiting the entire dopamine system. In fact, if we look at the brain of a rat who was attracted to the shock rod because of the amygdala stimulation, if we look at that rat's brain just after it's attracted to the shock rod, we see the entire mesolimbic dopamine system is activated at the moment the rat was being attracted to the shock rod. So it's telling us the amygdala is really taking control of the dopamine system. In this case, it's deciding what it is to be wanted. It's assigning incentive salience to the particular thing, to the particular shock rod in this case.
Yeah, I mean, it's just amazing. So once you do this, that system is entirely taking over, right? So any sort of rational things that might be going on in the brain is all sent to the background. It doesn't really have any effect, that it is wanting to continue to get shocked over and over again.
Yeah, it's definitely not rational. This is clearly a maladaptive one. And this is probably, after 30 years of this research, this is probably the strongest proof of principle demonstration we've ever had that wanting can be entirely separated from liking. Because here you're wanting what has no liking at all. You're wanting only what hurts you. But I wouldn't say necessarily that the rat wants to be hurt. It wants what hurts it, but it's not necessarily the same thing as wanting the hurt. The rat doesn't throw itself on the rod and try to get shocks. What it does, it's attracted by the rod. The rod, in a sense, is a cue for the shock, and the cue is becoming attractive. We know that it's the cue that's becoming attractive because at the same time that the rat touches the rod, we also play the rat a distinctive sound every time it touches that rod. So it has an auditory cue that means shock rod. Now, if we ask rats, do you want to hear a sound that's been paired with shock? That means shock to you. No rat would ever want to hear that. In the 60 million years that there have been rat-like creatures, no rat has ever wanted to hear a sound that meant shock. But these amygdala-stimulated rats will work to hear that sound. They want to hear that sound. They're attracted to the shock cue. Give it to me again. Let me hear it again and again and again. They'll work to hear it. These are the cues. Again, this is an incentive salience process. The cues are becoming irresistibly attractive, and that's what pulls the rat into the shock.
So do we see this in humans too?
Well, I think I wouldn't want to say that we see this identical maladaptive attraction that we're seeing in the shock rod, although it's possible that some instances of, say, self-harming behavior, self-cutting, and other forms of self-harm might involve this kind of process. But we definitely see in humans, we are attracted by the cues for the things that we want. The cues are very attractive and they can tempt us in. That's what advertising does. And sometimes it can pull us into situations we'd rather not be in.
Yeah, it's really fascinating, Ken. So this has a lot of applications, and we talked about some of them in treatment of addiction, treatment of certain CNS diseases, and perhaps other areas. So as you go forward in this research, in conclusion, Ken, where do you want to take this? What is the next thing for you?
Well, in my own experience, the research has been a series of surprises. We never expected wanting to be separate from liking. We never really expected the shock rod to become more wanted, even in this recent experiment. There have been lots of surprises like this along the way. So I would say, in one sense, I don't try to expect what's going to be found in our next research. We're looking, but we are always motivated by the goal of trying to better understand what are these psychological processes, what are their rules of operation, as well as what brain systems mediate them. Because we've learned we get surprises about the nature of the psychology as well as about the nature of the brain. And that's what I think will continue to happen. That's what we're looking for.
Yeah, I mean, the research is really challenging the assumptions that we hold, right? And when we have those assumptions that strongly held, that has implications for how R&D is done, let's say in pharmaceuticals and other areas. So challenging those assumptions, I think, has long-term implications as to how treatment modalities might evolve in this area.
Well, we simply want to understand what is true, what is really true. And it is the case that sometimes our hypotheses can misguide us. So we have to test them, and sometimes we find new hypotheses that turn out to be better.
Yeah. Excellent. This has been great, Ken. Thanks so much for spending time with me.
I've enjoyed it. Thanks for the conversation.
Yeah, absolutely. Good luck with this research.
Okay, bye-bye now.
Okay, bye.
Okay.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.